So in our second lecture on manifold learning, we will focus on learning slow manifolds in dynamical or time series data. What does that mean? So first of all, there are very different types of time series or dynamical data, and therefore different notions what slow could mean. So for example, we could have deterministic dynamical data, such as the motion of a pendulum. Or we could have data where there are stochastic fluctuations, but there are underlying deterministic regularities. For example, consider a signal that measures the temperature anywhere on Earth over time. Now, this signal can be described by a time-dependent array of temperature measurements of different locations on Earth. And the signal will be stochastic because there are random variations of the temperature or variations that are hard to predict. But there are underlying periodic oscillations, for example, the day-night cycle and the annual cycle. So if we are asking for a slow component of the dynamics here, then we could, for example, say the annual cycle, that is a slow component underlying these time series. And this annual cycle is completely deterministic. Then in addition to stochastic versus deterministic, there is also stationary versus non-stationary. So what does that mean? For example, in the global temperature, there are stationary and non-stationary components. The daily temperature cycle in a certain location on Earth will fluctuate between the day and night temperatures, but these temperatures will scatter around their respective means of the corresponding month of the year. And then the annual temperature cycle will cycle between these different mean temperatures in the corresponding location on Earth. So we can assume that a model which describes the temperature changes on this time scale, so days to a year, is stationary. So that means it follows the same rules. However, if you observe the annual temperature cycle over many, many years, this is no longer true because there is climate change. So there is a general increase of the mean temperature if you look at it over the last 50 years, let's say. So that means you cannot use the same model for every year in these 50 years because the means are changing. So you have an overall drift or a non-stationary component of that data. And another example of such non-stationary data is stock market prices, for example. So in stock market prices, you typically have trends. So often you have fluctuations around linear up or down trends. If you look at the Dow Jones or the DAX index over the last 20 years or the last 50 years, you have a very strong upwards trend, but then there are often on shorter time scales down and up trends, such as during crisis, such as during the financial crisis or the COVID-19 crisis. And then there are similar changes between down and up trends on shorter time scales, for example, on a month or day schedule. So in all of these examples, you have different processes on short and long time scales. So there's different things we could mean by what is slow, and we have to specify which type of process we're talking about if we want to solve a learning problem for that. Surprisingly though, these quite different problems can often be cast into very similar learning problems. But this is not a lecture about time series, it's a lecture about manifold learning, so I will focus on one particular example here, without going into much detail how that can be related to other cases of time series. And the case that we are looking at here is the case of stationary stochastic time series. And here's an example of what I mean. So this is a time series of a stochastic process, so this could be a stochastic oscillator that oscillates between two semi-stable or metastable states. In natural sciences, an example of something like this is protein folding, where you have a molecule, a protein molecule that can be in two states, folded and unfolded, and it likes to stay for a while in either of the two states, but there are stochastic fluctuations, and eventually there is a transition from folded to unfolded and from unfolded to folded. And what you see here in this time series is that you have over time, the system is either in the blue state for some time and fluctuates around it, or in the red state for some time and fluctuates around it. And there are rare transition events between these two states, and they occur after random times. So there is a randomness how long the waiting time in either of these two states is, and there are occasional transitions between the states, but when these transitions happen, they happen fast, but they happen rarely. So in this sense, slowness corresponds to these rare transitions, not to the fact that transitions themselves are slow. They are not, they're just rare. And what is our learning problem in this case? So our learning problem is find a representation of the system in which these rare events can be well described. So in the plot in this figure, you see a one-dimensional time series, but of course we're interested in high-dimensional time series, so high-dimensional systems that we trace over time. And now we are asking the questions, what are the coordinates or representations of the system in which we can observe this behavior? So in the simplest case, we are looking for a linear projection denoted by a vector W, on which the system state can be projected such that the rare event processes can be easily traced, like in the figure above. Or in a more general sense, we are looking for a function, a nonlinear function, f of xt, which projects our data or which maps our data to a manifold in which the rare events can be well traced. And well traced means where the long-lived states, so in this example the blue and the red states, are well separated or clustered. Okay, so this is our setting that we have in mind for this lecture, so stationary and stochastic. Nonetheless, many of the methods we are describing here can also be used for non-stationary and non-stochastic time series, but again, this is not something we will discuss in detail here. Like in the last lecture on principal component analysis and autoencoders, we will first use some conventions in order to say how our input data is represented. So first of all, we have a multidimensional data set over time. So we have some sort of arrays over time. The array characterizing the system state at every time point could have an arbitrary shape, but just for simplicity, in this lecture we assume that it's formatted as a vector of d dimensions. And the overall time series has capital T time steps. Now we use an important convention, which also in some sense restricts our attention to what our learning problem shall be. Namely, we stride the data, the time series data, into two time-lagged subsets. The first is subset X, which contains time points t equals 1 to t equals capital T minus tau. And the second one is subset Y, which contains time steps tau to t. Tau is a time lag that could be any natural number smaller than t, at least one, but smaller than t. So these two subsets can have an overlap. They can share certain time points. By formatting the data in this way, we have two things in mind. So first of all, the time tau is a so-called lag time. It basically is a time scale that defines what do we mean by slow. So slow or rare are events that happen on time scales longer than tau. Everything that is smaller than tau is considered to be fast or often. Secondly, by creating two such time-lagged data sets, we indicate that we are interested in a sort of Markovian picture. So we want to say what happened in Y given that we know X. In this lecture, we are not considering arbitrarily long histories in the time series. That is something we will consider in the next lecture when we talk about recurrent neural networks. But in this lecture here, we will always look at learning problems that are related to Markovian models. You will see more clearly what that means in a later stage of this lecture. Okay, given this representation, we will remove the means from both x and y in the same way as we did that in the principal component or autoencoder lectures. So we assume that the data is mean-free in the sense here if you just sum over the rows of x and y, and otherwise you remove the mean in x and y separately and define this as your new x and y. Secondly, I assume you have seen the last lecture on principal component analysis and autoencoders, and we actually use some of the results of this lecture here. So we apply principal component analysis to each of the data sets x and y. So that means we compute the covariance matrix of these data sets, perform principal component analysis. So we do an eigenvalue decomposition of this covariance matrix, and then we decorrelate and whiten the data. So that means you compute all principal components of the data set. So you consider all eigenvalues of the covariance matrix, and you define these eigenvectors to be your new basis. So that means you rotate the data in such a way that the first dimension corresponds to the dimension with the maximum variance, and the second dimension is orthogonal to that, and then amongst those directions corresponds to the directions of the second largest variance, etc. So in that we are going from the red representation on the bottom to the green representation. Also note the mean has been removed from the red data. But in applying PCA, we rotate the coordinate system such that the data cloud is rotated from the red one to the green one, so that the largest variance is aligned with the x-axis. And in a second step, we divide every direction by its standard deviation. And the standard deviations are just the square roots of the eigenvalues of the principal component analysis. So we can achieve this by multiplying the rotated data with the inverse of the eigenvalue matrix, or the square root of the eigenvalue matrix. And in this way, we scale every direction to have a variance and a standard deviation of 1, and we achieve this whitened data, which ideally looks like a Gaussian distribution with 0 mean and with standard variance. Now, it's of course not always a perfect Gaussian distribution. There can and usually are more complicated structures inside the data, but we will still achieve 0 mean and a standard variance of 1, and a covariance matrix that is identity. So all other features that in which our data distribution differs from a Gaussian distribution are in higher statistical moments. All right, so here's the summary of the data preparation. We assume coordinates are mean-free or remove the mean otherwise. We compute covariance matrices. The covariance matrix CXY will be needed later, but for now we only need CXX and CYY on the separate parts of the time-lagged data. And then we use these covariance matrices to whiten the data, and we call the whitened data X tilde. Now we define the learning problem that we want to solve, and it's important to understand that the result we will get, so the manifold that we will get out characterizing the slow motions or transitions or the rare events will depend on how exactly we do that, how exactly we define the learning problem. And here we do it as follows. So first of all, again, as in the PCA and autoencoder lecture, we will use first a linear model, and we will then later go to a nonlinear model. So we'll first ask the question, what is the solution of the linear problem when we have a linear projection to define the manifold, like we did that for principal component analysis. So what is the time-lagged correspondence of principal component analysis? And for that, we take first our data X and we search for an encoder matrix E, which reduces the dimension and projects the data onto a latent space coordinate Z. And then we have another matrix D, a decoder matrix, which takes our latent space vectors Z and projects them back to the full space. And in this case, we call the resulting vector Y star. So first of all, that is a vector in the full space. It's something that we want to compare to our time-lagged data Y, but we call it star because it's not the true data, but it's some reconstructed data. For now, we describe E and D as two independent matrices. So we assume for the moment that E and D are independent, have independent parameters. But there are cases in which E and D will be related or share the same parameters, as we will see later. Importantly, E does dimension reduction, so it's a rectangular matrix. It has less rows than columns. And D, again, lifts the data to a full dimensional space, so it has less columns than rows. And we call the product of these two matrices KD. So the smaller d is here the dimension of the latent space, and this matrix KD has small d rank. So it is size capital D times capital D, but it only has small d ranks. As in principal component analysis, we can define different learning problems or different optimization strategies, let's say. We will also see that this leads to the same result as in principal component analysis, but we can view the learning problem in two ways. We can either try to minimize a suitable error. So the logical thing to do is here to minimize the reconstruction error in the Y variables, or we can maximize a suitable variance, and we'll see later what that means. So for now, we just look at minimizing the reconstruction or prediction error, because it's fairly easy to see how that will look like and what should be done here. So here we minimize the reconstruction error given by the difference of Y tilde, so the time-lagged data, and Y tilde star. So that's the reconstructed time-lagged data after taking X, projecting it down to the latent space with E, and then lifting it up to the original space again with D. So we can also write this as X tilde multiplied with K tilde. And here we use the transpose just because the column vectors in the beginning of this slide become row vectors in the data matrix capital X and capital Y. Okay, we minimize this error and we minimize it over the elements of K tilde. So we're looking for the best transition matrix K, minimizing this error. So as I indicated before, by using this definition of a learning problem, we are focusing on Markovian models. So K is a transition matrix which contains information about what do we expect as YT given XT. It's a linear model in time. Yeah, we take our data point XT and we use K in order to predict YT. We do not use other data points that lie before xt, xt minus 1, xt minus 2, etc. We only use one such vector. So it's a Markovian model. It does not use memory longer than one time step. And remember that yt equals xt plus tau. So if tau for the moment is equal to 1, assume that the time lag is just one time step, then this means this model is trying to always predict the next time step given the current time steps and not anything else, no further history. If we wanted to use additional history, then we will arrive at a different learning problem, and then we end up at things like recurrent neural networks or autoregressive models. That is not what we are doing here. Also, we have only one transition matrix k shared across all time steps. So we're using the same transition matrix k in order to propagate, let's say, x1 to x2, x2 to x3, xn to xn plus 1, independent of which time index we're talking about. So this is what I meant before when I said we're talking about stationary time series or stationary models in this lecture. So we assume that the parameters can be shared across time. All right, so this defines our learning problem for a linear parametric model at this point. And with this, we will pick up again in the next part of the lecture, and we will discuss which learning methods can be used to solve this problem.